Welcome everyone. It's 9:02 and in the interest of everyone's time, we're going to go ahead and get started. I'd like to welcome everyone to the fourth installment of Katia University. With this Katia University webinar series, we're trying to show you how to use some of the more advanced features in the Katia product offering. And today we're on our fourth installment and we're going to talk about design and manufacturing with composites. My apologies, additive manufacturing is not really going to happen today, but that's a topic that we'll bring up for the future. With me today is myself. I'm Susan Crowden. I have Glenn Larson in the background here. Our presenter for today is Etienne Ardois from Dasso Systems, and Danny Alcini is also here from Dasso Systems. Next slide, please. First, let's talk about the good stuff. Graduation gifts. Yes, we're having graduation gifts. We're expecting everyone to graduate with flying colors. So what we're doing is anyone that is on this particular presentation today will be entered to win a $50 Visa gift card, but you have to stay to the end to get that gift card. And then anyone who participates in all 7 classes, we've already started back in July of this year and we'll finish up in 2022, although we've got a lot of feedback from people saying they'd like us just to continue with this. So anybody that attends all the classes will be entered to win either a Space Mouse or an iPad. It'll be your choice. Next slide. So who is Vias 3D? Just quickly, I'll run through this. We're a Dasso Systems partner, and we've been a platinum partner. It's actually now the last 4 of 5 years. We're also a Dasso Systems education partner. We have multiple industry experience in many different industries, including oil and gas, nuclear, aerospace, manufacturing, and automotive. Our team consists of more than 100 employees with a lot of PhDs and high degree people working in design, manufacturing, structural mechanics, fluid mechanics, electromagnetics, optimization, reliability, data analytics, and system and hardware architecture. We provide engineering services, and we are a PLM consultancy doing training and software sales for the PLM products developed by Dasso Systems. We have a global presence in the United States, Canada, Mexico, a few locations in India, and we recently opened an office in Turkey. Next slide. Who is Dasso Systems? So I'm hoping that most of you know who Dasso Systems is, but if you don't, this is our university. We will let you know who they are. They're the world's leading developer of CAD/CAM and CAE software solutions with more than 120 interrelated software products. They serve 11 very vast industries, including transportation, aerospace, marine and offshore, cities, counties, and territories, business services, etc. They're enabling implementation of design, analysis, manufacturing, and post-production support systems. So we handle everything from inception or conception through obsolescence. I think 22,000 is a low number for people who are working at Dasso. I think it's higher than that now. With 12,600 worldwide partners, Vias 3D is one of the worldwide partners. They have more than 290,000 enterprise customers and are about 5.4 billion in sales annually. Next slide. Our value at Vias. What we do is we keep people connected for collaboration to foster communication and innovation. We wrap process discipline around these services to efficiently manage product development and change. And we create a digital product experience to simulate performance and assure quality. Digital transformation is achieved using the 3D Experience technology platform. Yeah. So the platform has social and collaborative apps, 3D modeling apps, simulation apps, information and intelligence apps, and it's all real time on one platform. So it's a single source of the truth. Next slide. I'm pleased to present our speaker for Katia University. This time we have a guest speaker from Dasso Systems. Next slide, please. I'm pleased to present Etienne Ardois, who's the Katia NAM technical expert. Etienne is a senior solution consultant for the Katia technical team at Dasso Systems. He focuses on design for manufacturing with composites and additive. And he comes from a material science and mechanical engineering education. His field of expertise is in 3D design and simulation, and he's got over 15 years of experience. Prior to his position here in America, Etienne worked in Europe as a design engineer and structural analyst at aerospace and automotive companies, and then joined Dasso Systems. He holds an MS with a specialization in composite materials and structures from the University of Bordeaux and the French Engineering School. Etienne, you can pronounce that for us. École Nationale Supérieure. Can you go?
Yep, Arts et Métiers. École Nationale Supérieure d'Arts et Métiers. Thank you, Suzanne. Should I take the
yes,
ball?
Take controls. It is
Okay.
Classes in session. Today you're our teacher.
Sounds perfect. All right, can you see my screen with the presentation on?
I can see it.
Okay, thank you very much, Suzanne, and to the whole VIAS team for having me today for this presentation. I'm very glad that I can take about 50 minutes of your time, about 45 minutes of your time to deep dive a little bit into what we have at Dasso Systems for composites engineering. So the solution we propose is really end-to-end. And again, the goal is to perform lightweight engineering. So lightweight engineering, that means actually the goal is really to generate parts that are as performant as possible and therefore the lightest possible with the best performance. And going composite has been a key for the industry to achieve this quest of lightweight engineering. So this is something that we have seen adopted massively in the aerospace and defense industry, especially with the Boeing 787 aircraft and then the A350 on the Airbus side, which were making enormous use, of composite materials for the whole aircraft primary structures, so the wing panels, the stiffeners, as well as the fuselage. For both of these aircraft, these were really the tipping point. And the goal was to generate a lighter aircraft so that it would be more fuel efficient. And especially now, those considerations of fuel efficiency and efficiency, generally speaking, will be even more stringent than before. So we see also a lot of composites in the wind energy business. So for wind blades, for example, and we see them also in automotives. So in the transportation and mobility industry, as we call it at Dasso Systems, as we classify it. So that means automotive, also to some extent in bus and things like that. And marine and offshore, also we see obviously composites in a defense vessel, but also of course on sailing boats and quite a large family of leisure boats as well are making a strong use of composite material. So usually when you design composites, so the challenges on the engineering side, the challenges are that you're gonna have different people in your company working in different teams who are going to use it, and they may be working with disconnected software, disconnected tools. And as a result, you're gonna have each individual in the company working in silo with their own tool. And typically that makes things very difficult when you need to exchange data sets. You may end up, as a consequence of using different tools and working in silos, you may end up with out-of-date data. So the other problem is that, so typically when you work with composites parts, with composites you can do a lot of some very complex shape because of the drapability capability of the fabric. So you end up typically with sometimes very complex surfaces, complex geometries, and requirement to produce the part. And if you don't have a set of tools that's gonna describe you explicitly in 3D how the part needs to be manufactured, you're going to observe a lack of repeatability, and you will not trust the result of you will not trust the part that will be produced. So typically those are all those issues that are making things difficult for the adoption of composites at the company. And an example of process at a company who is starting his journey into composites, where they have different people involved in composites, but using different tools, is actually a first good step of a company who may have adopted 3D, but typically results still in inefficiency. So what we propose is, first, the key thing is having a solution to do 3D for composites, having the surfaces dressed up with composites attributes explicitly, because the layups are complex, the surfaces are complex, so you can't really still get away with just some drawings and some Excel spreadsheet describing the ply table. You really need the ability to define in 3D the plies definition. And so this really having a true digital twin of your composites object. So basically the digital twin compared to what is in the shop floor. It's really key to optimize your time to market, time to produce, and to improve the quality. So you can anticipate any issue that may arise before production or before the part is in service. So you really have this ability to capture both the as design and as built by going 3D for composites. So what we propose is going beyond that 3D for composites, so the 3D experience platform that's going to include not just the design tool, but also all the manufacturing tool, as well as the structural analysis tools, and everything, and as well as manufacturing, embalm, and everything. So proposing the entire workflow in one platform, so you don't need to exchange data back and forth, going from your CAD tool to the FEA tool or to external software. You are able to roll the entire workflow in one place without having to exchange data. You just open the data on the platform in one app or another. And it can start at the conceptual design level, where you start to have a very raw idea of how much layers of plies you want in one area. So the laminate thickness in each of the area of the component you're gonna work on. All that, of course, is driven by performance. So typically structural analysis performance. So stiffness, or this can be stability requirement, or this can be a frequency requirement, linear dynamics requirement. And of course with a weight target. And starting from those requirements, then Katia, the software, the 3D experience platform, will let you iterate in order to achieve to reach the correct definition, to make sure your parts in order to reach the correct definition of the laminates. And then we can start to move forward, and instead of having just a view as a laminate, to turn that view into plies, into conceptual plies first, and then to actual plies generated as wireframes, which you can then manipulate. You can control how the drop-off are managed when you go from one thickness to another. And you can use this accurate digital twin, so the digital twin of your composites definition, to be used for virtual testing. So you can really take your detailed design in 3D and generate a ply-by-ply model on a 3D finite element model. Of course, as we iterate into the digital twin and doing virtual testing, we'll also want to ensure the feasibility. So there's a set of tools in CATIA as well as some technology developed together with Abacus and Katia that allow you to simulate the manufacturing process, whether you're going with hand layup or whether you're going with forming or fiber placement. We can simulate that process in the platform to ensure that the part that has been designed based on performance requirements, that has been ensured, certified in terms of those performance, can also be manufactured. So of course, it's not, I've shown that here as sequential, but being on the same platform using a unified data model means that you do not need to work in waterfall. So you can really start to work early on the same data model and just simply update your simulation or update your downstream models just as the master model gets matured further down. And finally, so manufacturing. So this is really once the part gets released, once the part has been assessed for manufacturability and that the structural performance were met and the part has been released and approved, as then also you have all the capability to generate the manufacturing resources, I mean, to simulate, to run the offline programming and simulation of all the equipment in your manufacturing shop floor and to generate the production data. So we are also working on generating a manufacturing bill of material and process planning for composites. So that's also possible to do in order to prepare your manufacturing processes in a very, very nice and clean way. But the entire solution, as you can see, is there. It's available in one platform, and that's really what is changing the game. And again, so we do support multiple manufacturing process. So whether we're talking about hand layup, automated fiber placement, or forming, we can do it. We can simulate the process, ensure the feasibility, and generate the downstream and generate the necessary data in order to manufacture the part effectively in the shop floor. So whether these are flat patterns, so the ply kit, as well as laser projection program, we can do that. Or whether it's about simulating an automated fiber placement machine and generating the G code, we can do that as well. One other key also is that so not only we offer a platform to have an explicit 3D design of plies, but also once you get those plies designed in 3D on the geometry with many complex refinements, as you will see deeper, we can also plug directly, automatically have a structural analysis model generated and associative to that 3D model. So it's really changing the game in that mindset, is that so you have one master model, this digital twin is truly driving the design stages, is going through the design stages as a master model, but you have many different connected models, such as, for example, a structural analysis, which can be connected to this master model and gets updated as the design model is changing. So it's really a new approach because that allows you to have, let's say, if you have a surface change, this would be reflected automatically in your CAE model. And same thing, so instead of having the CAE model where you refine the ply definition, the laminate definition, so here you start right from scratch in the same CAD design tool. You have already your laminate definition and all the thickness requirement. It's all there. So you do not need to do back and forth exchange between structural analyst and design engineer because everything is at the same place. So first you define your laminates on the geometry and then you map them onto FEA. The mapping is done automatically. The big advantage as well is that not only it can work at a conceptual level, at a grid design level, we We'll see a little bit more about what this means. But you can also do it at a very accurate level when you have the plies, including the fiber simulation. So once you have all the accurate fiber angle that's been calculated by the draping simulation, this can be mapped over into your FEM. And one of the key value of the platform is that not only it's going to connect different people working together, but also it's going to provide those 3D data to people who maybe were not using any 3D design, any 3D engineering software before. So why? Because we are providing the accessibility to the composite data directly from a web browser. So you just need a web browser and of course being granted access to the data on the secured platform. So that's the key. But as long as you have this access granted and you just have an iPhone or any kind of device that has a web browser, you would be able to access to those composites data. And what I mean, so what you see this screenshot here, this is the view of what you have access to when you are from a web browser. So you have access to the full ply card, so it's a digital card where you have the area coverage of the ply, the weight of this object, and of course the material, the direction, the name. But you also have as well access to those core samples. And core sample, which are basically, if you click in one area, it's going to tell you what's the thickness, how many plies there are, and how they are arranged together. So you just click on one of those labels, and you will have this 3D view of the core sampling that will be showing up in the panel. And you can, of course, review also the cross-section. So if you have created a cross-section in 3D in Katia, you would be able to see that in the web. So it's changing the game because that makes people, it can be used originally to do design review, but it's also very powerful potentially to make sure that the 3D data definition is gonna be available for people in the shop floor. So if you, in the shop floor, typically you may have just an iPad or something like that, or a screen, but you may not have a computer that's going to be used. I mean, at least not when you are manufacturing the part. You probably don't want to have a computer for designing, for authoring the part. So here, having such a tool will allow people to be able to check the information, to check the data as they were intended to be manufactured. This can also be used not just during manufacturing, but after manufacturing for maintenance and repair operation. So any questions so far? Let's have a quick look on an example part where we're gonna go through the entire process. And then I will do a deeper dive on each of those steps. So this example really starts from scratch, where you start and create a geometry from some NECA curve. Then we have the geometry. We're going to define some reference elements. And what we do in Katia, we do what we call a grid. So the grid, basically, this is defining regions. So geometry, we are using geometry lines in order to split the full surface into sub-regions, into cells. And each of those cells will then be associated with the thickness. Once we have each of those thickness associated, we can generate plies. Why? Because we have some drop-off areas. You see, when we go from one thickness to another, we do it gradually with a ramp. So the nice thing is this 3D object in the platform can be used for any kind of simulation. So here, for example, you see a CFD simulation, but obviously we would want to use also those structural properties for a structural analysis. So supported process, so it's not just hand layup, it's also liquid molding and automated placement. And here, that's what we're gonna do. We're gonna simulate the fiber. We're gonna do some fiber simulation on each of the plies, and we're gonna generate all the flat pattern. From then we can generate plybook drawings basically, and we can also generate a laser program or even simulate a robotic fiber placement tool. So we support also some dedicated processes such as, so this is pool braiding. We support also, we have an app for forming, for the forming process simulation. So we did quite some extensive work on those two processes, which have the potential for high volume production as well. And so yeah, and so we've been this software has been in use successfully at Boeing, Airbus for quite a number of years since the programs I was mentioning before, 15 years ago. So, and we continue to improve and to gain new markets and try to follow the trend. So you will see this is a very comprehensive suite of tools. So how it starts? It all starts basically, so this is the beginning. First, you need to have a material created in your database. So I'm assuming most of you are familiar with the 3D Experience platform. But so if not, the first step when you are in CATIA for structural analysis, for Simulia, or even if you want to do a weight analysis, you need to have a material defined. You need to have this material object created in the 3D Experience platform. And this material object has properties like density, but then has some specific attributes gathered into domains. So, well, there's the domain dedicated for composites. So if you go with the composites domain, you're going to be able to define, to assign those attributes that are going to be used by the composites application. Same thing, so you will want also to have not only the manufacturing and design view of those composite materials, but also maybe their structural properties. So where you define all the elastic properties in two directions, the E1 and E2 that you can see here, are defined here in this material card. That's really, basically, it's an abacus card. The nice thing is you define everything in one place. It's one single source of truth. And then we're going to use this material assigned to the geometry through what we call apply. So you can create apply manually simply by selecting a surface, selecting an axis system that's going to indicate what is 0, what is 45, 90, and so on. And then select a wireframe on that surface. And that's it. You have apply. You just need to assign it a material and a direction. And direction are specified based on that axis system. But yeah, so you need to have a material first, and then it's very fast to create manually a manual apply. Simply by selecting a geometry, so a wireframe on the surface. And we can copy paste applies to generate as many as we want. So another smarter method when you have like some fairly complex design, typically a grid design. So it's especially when you have a skin panel that's constrained by some reference stiffening elements. Example of the wing skin panel, where we have ribs and spars running underneath the skin panel. So we have this skeleton with all the reference elements. This is what we're gonna call the grid or the grid panel. And then we're gonna address this grid with all the laminates, and that gets us the full grid definition when we have not only just a skeleton, but also the laminate definition, the requirement in terms of thickness, that gets us the grid. From then, we can take this grid and ask the software to help us to generate plies. And plies, this is what I was referring to. This is basically a complete wireframe that's defining a region and that's associated with the material and an orientation. So this is how it works, basically. So you have the conceptual design. And the conceptual design, basically, you don't know how the plies are gonna be arranged. You just know how many layers you want in an area. And now you move into detailed design, which is basically you say, okay, Not only I know I want 4 layers here, but I know I need to start with some 0 carbon and then put my Kevlar in between and then wrap this up with the 0 of carbon. And then in this other area where I just want 2 0 carbon, then I want to ensure the continuity of my plies going from one area to another. So you see, so the difference is basically having a very conceptual view just from a structural performance mindset into something where you really have your true digital twin of your composites model as it's going to be made in the shop floor. And really not only how it's been made in the shop floor, but how it's going to behave later on through the whole life cycle of the part. So this is what I mean by digital twin, is the actual ply representation. So Katia is the grid design is gonna help you to cover this transition from conceptual to detail. And of course, throughout this transition, there may be some changes that you will be making, and you will be potentially managing the drop-off, maybe changing your mind here, how many layers you want in this area, and then you have to update the detail model. So all of that is possible to manage with Katia Composites. So once you have your full ply digital twin model, there are many things you can do with it. So you can, of course, prepare for manufacturing, and we'll talk on that. But you can also manage, if you have also done the structural analysis in real time, but you can also just review those models for design and approval review meetings, for sharing with other people who are gonna be involved in the project. So you can just simply click on the 3D plies and you will have this view as a material ply table. So the nice thing, it's not just an Excel spreadsheet, because if you click on one line, it's gonna highlight in 3D the location of the ply. You can also generate cross-section out of the surface. You can also generate core sample like I was talking about earlier. You can check the weight. So we have some very accurate tools that's going to give you the weight and balance information for a given part. You can also, so as I say, the plies are defined by wireframes on the surface. You can generate solid, or you can also generate one surface for each ply. Not recommended, because it's gonna, if you have 500 plies in one part, it's gonna be a lot of surfaces to handle. It's gonna be very cumbersome. So this is why it's much better and much more efficient approach to have just wireframe on the surface and generate the cross section when you need to view what's happening. Any questions so far? All right. So I will
take the questions at the end. There are some questions, but let's take them at the end.
Okay. All right. Sounds good to me. So yeah, so what I meant basically, so this is, here I'm from the web, you know, so this is Google Chrome. I'm connected to my platform, and I have here this dashboard that I created. And on this dashboard, I can simply just call for a couple of applications, like 3D Annotation Insights is one of them. And let's do that. So let's say that I'm gonna create up. I'm gonna decrease that. So I'm gonna decide the platform I'm gonna search my data on. And I will just, for example, I've been notified that I need to work on a specific model. So I can simply go ahead and search for that data called, let's say, winglet, for example. I search for that. So I'm searching in my database, that's the platform that's internal to my company. And let's say that I have this one. And I'm gonna just simply drag it and put it directly from my web browser. So I can do that from my computer, but obviously I could do that from an iPad or any kind of device that's supporting a web browser. So the nice thing is I'm supposed to have, oh, okay. So let's take this one I have already opened. So the nice thing is if we have the plies already created, because this model has the plies created, the one I just opened didn't have the plies. So if it has the plies created, then you would be able to review all those entities directly from a web browser. So for example, you can review all my plies 2, 3, 4, 5, all the way up until 48. You can review each of them directly from a web browser, and that really makes a significant difference. So let's say that you need to give your approval on those sort of design, then you can basically do a virtual review on that at this moment. One other example would be on here. So on this one, you are able to do some annotation as well, some markup. So you can specify if there are some areas that needs to be changed, that needs to be reviewed. You would be able to specify that in a 3D window. And so the nice thing is once this is created, once this is reviewed from the web like that, then you can simply just drag and drop this object and drag and drop it into the actual Katia client, which is the more like the software that's a little bit more heavy than just a web browser. The software where you can create your geometry, and here in that case, assign your laminate definition. And so we have two choices. So we could say, okay, that I want to create just simply, I want to create plies, and I'm just going to use this grid panel definition. So that would be possible. How to start your composite design? So you have your composites parameters first, where you have the list of materials, so you can add other materials from your database, the list of direction, the rosette that can be specified, guided by a curve, or that can be specified just simply by picking an axis system. So as you can see, you can have a clear view of how the orientation, where the orientation will be described, how the orientation will be mapped in each location of the surface. And once you have all those main parameters, which are going to be used for the entire part, then you can go further and define simply a ply. So to define a ply, you can simply just create a ply manually. Oops. You can create a ply manually, first by defining a new ply group. And then creating your ply. I have some updates going on the other 3D section. Okay. and then going ahead and creating a ply so the ply definition, like I said, basically you just need to specify the contour that you want. So this can be as simple as picking some wireframe, you know. So I'm gonna just pick a couple of wireframe like that. Yeah, maybe not this guy. I'm gonna pick a bigger one. Up. And as soon as you are closed, you know, so now we have all those 4 wireframes that are defining a closed area. Then you can just specify the material you want, the direction you want, and that's it. You created a new ply. So it can be as simple as that to create plies, or you can do a little bit more refined approach where you have, excuse me, where you would have the grid definition. Sorry. Where you would have the grid definition. And the grid definition, basically, it consists in defining the areas, and each area will have a certain laminate. And so those laminates do not have to be, you don't specify the order of the layers. You just say how many layers you want in a specific area and how many layers of each direction of each material you want in a specific area. And that's what is defined at the level of the grid. So once you have this conceptual view, then you can turn this conceptual view into something that's going to be a first step into the plies definition. This is what we call the virtual stacking. And this virtual stacking basically is going to give you a better view on the ply map as it's going to be created. And so this is the software. This is where the software is extremely helpful, because the software will help you, will propose you some design based on the laminate requirement. It's going to propose you group of plies. So the software will propose you how to assemble together regions in order to form plies. And that's really is extremely powerful to turn a conceptual view, a finite element analysis model view, into something that's going to be manufacturable. This is really extremely important. So an important point also, composites, so you have all the ability with the review tool to perform numerical analysis. If you just simply double click on the stacking, you would be able to review all those plies. As I was saying, you can review now all those plies. And they are highlighted in the 3D, and they can even be showing up in a separate window like that here. If there's a flat pattern computed, that would show up as well. So you have this view, this stacking table that really helps a lot to control the digital twin. We are also, of course, able to create cross-section, like I was showing earlier, you know, so can be extremely helpful in order to review better what's happening, to understand better the design of your part. So you can perform cross-section, you can perform obviously as well, so core sampling, which is again, so core sampling consists in providing you a view in one area. You have the clear view of all the plies that are located at this area. So it's extremely helpful for maintenance and repair, but also for quality insurance. And it's very important also to use through the design concept, through the design stage. So let's come back for a minute. I realize time is flying. I just have 15 minutes left. So if we come back now on the deck of slide, let's have a quick overview of composites manufacturing. So what do we do in CATIA for composites manufacturing? Well, first we take those plies which is the first level of refinement from conceptual to something that actually exists. And then we're gonna prepare those plies to make them manufacturable. So typically there are several considerations in composite. Is that first, while we always trim the plies after they are cured. So what you want is going to have on the shop floor on your tooling a little bit more material than what you will have in the end after the edge trimming. So you're gonna do what we call material excess. So that's why we have an engineering edge of part and a manufacturing edge of part, and we provide tools for that, for extending those limits. Also, another thing is that there's during the curing and actually after the curing, when the parts get debulked, we find out that the part is like shrinking and warping a little bit compared to the tooling. So due to various phenomena like the difference of CTE between the materials, unbalanced laminate also can cause some effects, or maybe any kind of cause that would lead to some imbalance in terms of stresses inside the part is going basically to generate those warping, shrinking phenomenon that you see on the composite part. So what we do typically, we have a compensated tooling surface and we swap the definition of the ply from the engineering surface to a compensated tooling surface. Simulate also, so for fiber simulation, we can do draping simulation. We can do simulation also for other process, like braiding or like fiber placement. And typically, if you do hand layup, the next downstream of thing that you want is the flat pattern. So in order to prepare your material kit. And before going there, sometimes, the material roll is too small to fit an entire ply, so we need to do some splicing. So we do have tools for that as well for splicing. And then we can generate the outputs, the XF files for nesting, or this can be a 2D ply book. Although now, as you have seen, now you have the access from 3D, you may not need a 2D ply book. And laser projection code. So a key aspect of the software is really the capability to do fiber simulation. So fiber simulation, basically, this is you pick a point that's going to be the first point in contact between your ply, your piece of cloth, basically, and the tooling. So the first point, the application point, if you change its location, as you can see, it is going to change dramatically if you can make the part or not, and also, of course, the shape of the flat pattern that's necessary in order to drap this part. So what we offer in the software is some dynamic draping capability that's pretty unique, that's gonna let you just navigate through and try different area for this first point of application, in order to find what is the best to make it work in the shop floor. We can, of course, once we identify what's best, then we can review it with the shop floor operator by replaying the simulation. So an example of this seed channel, where we're gonna do and start first to drap the web and then drap all the flanges, so it's always very helpful to review this kind of simulation with the shop floor to ensure that everyone is in agreement and that it's feasible. And we can, of course, the seed point location, how to find it. You can look around on the surface to try to find the best location, the best position. Or you can also use our algorithms that's going to propose you an optimized solution. So seed point angle optimization based on minimum sharing. So the software will try to minimize the sharing. Those red area will be minimized, and it will find for you the best location of the seed point. Okay, so maybe I will show I will come back on the software. Up. All right, as time is flying and I want to make sure that we have time for everything. So I will go fairly fast. I won't have the time to demonstrate everything. So I have here this full ply. And as you see, so this full ply would be too complicated to make. How do I know that? It's basically, so I'm gonna go from my Katia Composites Design app. I will move over into Composites Manufacturing Preparation app. And I will go over here and do producibility for hand layup. So I'm gonna check, is this producible? Is this manufacturable? And I have this panel here, producibility for hand layup. I'm gonna go and click on indication and try this. So what you're gonna see here, this is fiber simulation. And as you can see, so this is quite a problem here, what's happening, you know? So obviously, it appears pretty obvious that it's gonna be very, very, very difficult for me to make this part. If I want to make it in one piece, it's going to be very difficult due to the complexity of the geometry, you see? So if I locate my seed point over there, then I can't even run the fiber simulation. So, and even if I locate it, yeah, so the maximum shear strain is too high. So basically, so what that tells me is that I won't be able to make this ply in one. So in that case, what I went ahead and did, I went and did the splicing, basically. So splicing, it's about taking a full ply, defining the curve that are going to be used for the splicing, and defining how much overlap you want in each area. And instead of picking just one ply, you're gonna pick several of them. Like for example, here I have 4 plies that have been selected, 3 splicing curves that are actually here, here, and there. And what this tool did, it generated all those sub-plies. So from my conceptual ply now, I have those sub-plies that are possible to make based on the size of the roll and based on the feasibility, based on the manufacturability. And if we want to take a look at this one, for example, so we can just run the fiber simulation. And I'm gonna just move around the location of this seed point. And as you can see, so live, my flat pattern gets updated. So extremely powerful capability. And of course, I could just simply go ahead and use optimize to have those optimization technique available in order to minimize the sharing. So minimize the sharing basically. So this is minimizing how much red area I have. Yeah, so this example is not appropriate as it works pretty well. So let's have a look on this one, which is a little bit more tricky to manufacture. So minimizing those areas where you see where the ideal rectangle starts to be too much diverge too much from the ideal rectangle, and you start to have those angles that are what does too much sharing basically. So too much sharing, this is what is measured as a critical condition for the fabric to be able to drop onto the surface. And once you have this fiber simulation, basically you have a discretization in 3D of the part of the clothes, and we can take this discretization to transform it into ideal view. So turning back all those shared angles into like square angle, and we get the flat pattern generation. And the flat pattern generation can be done for one ply or a bunch of them. And once you are there, then the next step is to export that. So for example, here on this little rib, we'd be able to go ahead and just simply export all those plies over for nesting and cutting into the ply kit. What we can do also, I will come to that in just 1 minute. What we can do also is typically to be able to take one ply, for example, here, and generate all the plies and have the software to generate for you the laser projection code that are going to be used for the laser projector to display not just the ply contour, but also any sorts of annotation that you may have associated with those plies. And you can export that into various laser projector formats from Virtec, from Faro, LPT, Align Vision, LAP. So we support a variety. And this ply kit here can be exported over into the XF format. So typically we support also IGS 2D, but typically all the cutting system are going to read in the XF files. And so this is what we do. So I mean, I know it's kind of a lot to absorb in just 40, in just a small amount of time, but maybe it's time at the moment to take some questions. What do we think, Suzanne, Glenn?
Yes, let's take the questions. We'll leave you on because you might have to show some things. So here's the first question. You mentioned digital twin and platform often in your presentation. Can you explain those two topics in a little more detail?
Oh, yeah, sure. I mean, so the platform, this is the actual software that we are using. This is the platform is basically the collection of all those applications. It's like an operating system, but for engineering software, if you want. And so I'm gonna try, yeah. All right. And so basically, so this is this unified infrastructure that connects all the apps developed by CATIA and now SolidWorks, and as well as Simulia, which includes all the Abacus team or Delmia. So all our software company involved in design, simulation, manufacturing, or any other discipline or supply chain, and of course PLM. So at the foundation of the platform is a strong PLM foundation. Being able to trace your data is key. Up, there we go. Oh, I wanted to show that. And so this is the platform. So the platform is this infrastructure that's gonna be able to let you connect all the apps from various disciplines. So this is the platform. And this is also what enables the digital twin. It's because basically it's like a virtual universe. I know the term metaverse nowadays is becoming more and more interesting, and but this is what we do for engineering and manufacturing. We do metaverse for engineering and manufacturing somehow. And this is what a digital twin is. Basically, you have a full description of your part, how it's designed in 3D, with how it should be designed, how it should be performed, so that's the virtual testing, and how it's gonna be manufactured. All that happens virtually before in the physical world. And this is what we mean by digital twin. Then there's also the concept of digital thread, where you have all the apps that can coexist together, where you have all actors acting live, acting concurrently on live data, and this is a digital thread. So all of that really is all enabled by the 3Experience platform, because it's one unified infrastructure for all apps. So I hope I'm not too conceptual on that, but I mean, there are tons of examples to illustrate.
Okay, here's the next question. How do you define a hybrid braided fabric, such as triaxial and biaxial fabric regions on the same ply layer?
So the ply can only be either biaxial or triaxial. I mean, otherwise you have two plies. But we can totally define, we have some latitude in the fiber simulation software to specify some material models. So I'm sure that depending on what you want, we would be able to do what you are looking after.
Okay, here's the
I think
next
this question would have to be dig further. Yeah, so those are those algorithms that can be used, and you have some material models also. You can go from bidirectional to more one-directional. And for triaxial, we have some other algorithms that may be interesting. But one thing I want to say is that so it's really intended for biax and UD. So we don't have a triax specific material model.
So I'll make this statement. If anybody that's asking questions needs more clarification, we're happy to do, a personal deep dive with you. So we're going to show towards the end here our email addresses, etc. So if you want to reach out to me, I can facilitate getting the right people in the room with specific questions that you may have, because obviously you've got something in mind here that I'm not sure what it is, but we can probably get to the bottom of it. So I just want to make that statement. Next question. Can you accommodate laser projectors, and what projectors do you support?
Yeah, so laser projector, as I was showing towards the end of the presentation, so we can propose a good solution to simulate where you're gonna locate them in order to ensure that your part can be displayed with one or two or three or as many lasers as you want. At least you know how many lasers you're gonna need to display your part, which is pretty good. And we also, of course, allow the system to generate the plies contour with the offset of the previous ply, which is very important. Otherwise, you're gonna have quite some glitch. And as well as any text information that you may want. And we can export that in various formats. Virtex is one very popular format, but we also work very well with other vendors like Align Vision, formerly Assembly Guidance. We do work very well as well with Faro LPT, and of course with LAP, but they are more common in Europe, although they are also in the US. It's a German company. So those are the four main that we work. And what we found out is that if you have a laser coming from another brand, usually they are able to read in one of those formats. So typically Virtex format is quite often the dot ply is quite often readable by most of the laser brands. But we do have native format for the four major laser brands.
Okay. Do you have any products to improve or analyze mold flow composite parts?
Are you talking about RTM? Parts that are going to be made with RTM. So we do have tools for RTM simulation, but they are not in the platform at the moment. They are with partners. So what we do typically, if you want to simulate the RTM process, the resin flow, and how it's gonna be absorbed by the fibers, and how the resin will flow from the inlet to the outlet. So this is something that's done outside the platform, and we can communicate the composites definition through various formats, typically FEM format. Usually that's how it's done. So that's the specific for that. We can, something I would encourage if there's a specific question, something like that, so we can totally have a separate conversation to follow up.
Absolutely. And then the last one is, does Katia have any apps for nesting?
We do not have nesting ourselves at the moment for composites. There's a beginning of nesting for the structural packaging app, which I think Vias is going to present you later on next year. So for composites, we do not have a nesting solution. We work closely with a partner, a software partner named JetCam. And we have a direct, if you go to Composites Collaboration, you can actually go ahead and export the data as the XF and XML. And this XML file would be read in JetCam, so you can retrieve all your plies and their attributes, as well as, of course, all their geometry for nesting. But that's not done in CATIA. It's inside JetCam.
Okay. So, Glenn, can you take back over the screen? That's all the questions that we had. I want to.
Absolutely. And I'd like to make a comment. I mean, what a good presentation. I got so much good information out of it. I loved some of the automation on the nesting and the meshing and the material. It's just great stuff. Thank you.
Thank you, Glenn.
Okay.
Yes, thanks, Etienne. It was awesome. But let's put it up there. The next slide puts our email addresses up there. So if anybody wants to get in touch with any of us, you can email me. I'm Susan Crowden, and I'll make sure that it gets out to the appropriate parties, and we'll sit with you and go over anything that you have in more detail. Okay, next slide. Now we're on to the winner. Kenya, do you have a winner for us? Oh, we can't hear Kenya. Can you send me the name of a winner? I can't hear you. She's saying Daniel Mendoza is the winner. So quickly, I'm hoping Daniel's still here. Quickly flash back to, yeah, Daniel, reach out to me, Susan Crowden, scrowden@viascorp.com, regarding your $50 gift certificate. That's so awesome. Next
Congratulations.
Slide. Yeah, congratulations, Daniel Mendoza. So our next class is not going to be until January 22nd. Just due to the holidays, etc., people are off and not interested in, well, they're interested in other things at that time. So the next class we're going to offer is going to be January 22nd, and it's going to be CATIA for packaging. If you guys want to put in the chat window or in the chat, any other topics that you might be interested in moving forward, we've decided we're going to continue this university concept into 2022 and, keep educating people on what these software packages can do. So please go ahead and do that if you would. And then next slide, it's just a thank you everyone for attending, and hope to see you soon at the next CATIA University. Thank you so much. Bye-bye.
Thank you for having me. Bye-bye.
Yes, thanks, Etienne. The presentation was awesome, very informative. Thank you so much for taking the time to present to the people here today.
My pleasure. Have a great day. Bye-bye.
All right. Bye, everyone.